Ever wondered how an AI could learn to solve any problem without being told exactly what to do? That's the wild world of zero-shot reinforcement learning, where an agent learns to master all possible goals, not just one. But here's the catch. How do you teach an AI to explore effectively when you don't even know what the right goal is? Let's break this down. In traditional reinforcement learning, an AI learns by trial and error, guided by a specific reward signal, like a robot learning to walk by getting points for staying upright. But zero-shot RL is different. It's like giving a chef a kitchen full of ingredients and saying, "Make any dish you want." The AI has to figure out all the possible recipes or policies without being told what to cook. The problem? Exploration. How do you collect data in a way that lets the AI learn everything? Most methods use separate exploration policies to gather data, like a robot randomly moving around. But this approach is like throwing spaghetti at a wall. Some stuff sticks, most doesn't. The key insight here is that exploration itself should be guided by uncertainty. Enter epistemic uncertainty, a fancy term for how unsure the AI is about its knowledge. Imagine a robot navigating a room. If it's uncertain about what's behind a door, that's where it should focus its exploration. The researchers behind this study realized that by minimizing this uncertainty in their model, they could make exploration way more efficient. Their tool: forward-backward FB representations. Think of these as a map that splits the environment into two parts, where you are the forward part and where you want to go the backward part. By combining these, the AI can encode all possible optimal policies in one go. But here's the twist. They didn't just use this map, they used it to guide exploration. How? They trained an ensemble of models, like multiple AI experts, working together, to track uncertainty in the FB representation. When the models disagreed, that meant the AI was uncertain, and that's where it needed to explore. It's like having a team of scouts. If they all point to different directions, you know you're in uncharted territory. The results? Their method learned effective policies faster, and with less data than previous approaches. In tests on complex environments like robotic control tasks, their AI adapted to new goals in record time. And because they didn't need to balance exploration versus exploitation, a common headache in RL, they could focus purely on learning. So what does this mean for the future? This work could revolutionize how AI learns in real-world scenarios. Think self-driving cars, personalized medicine, or even creative AI. By making exploration smarter, we're not just teaching machines to solve problems, we're giving them the tools to discover problems on their own. Now, let's dive into a specific study that tested these ideas. Researchers asked, how do different exploration techniques affect an AI's ability to learn new tasks? They compared two approaches, FBEEQ-SAMPLING, a tried-and-true method, and a newer one called FBEEQ. The results? The new method holds its own, but there's room to grow. Think of it like a student taking a test. Even if you're smart, you need practice to perform your best. The team thinks the small gaps in performance might be because they didn't spend enough time tweaking the AI's settings, like how fast it learns, or how it balances trying new things, exploration, versus using what it already knows, exploitation. Looking at the data, we see zero-shot scores, how well the AI does on tasks it wasn't explicitly trained for. The x-axis shows environment interactions, or trial and error steps, while the y-axis measures rewards. The shaded areas represent variability in results. Tighter bands mean more consistent performance. What stands out? The new method, FBEEQ, keeps up with the old favorite, especially as the AI gains experience. But here's the twist. When comparing two exploration strategies, F uncertainty, confidence in predictions, versus Q uncertainty, guesses about future rewards, the results change depending on the task. For example, teaching a robot to walk might favor one approach, while navigating a maze could shine with the other. This shows there's no universal best method. The right strategy depends on the challenge. So what does this mean? It suggests that fine-tuning how AI explores could make them smarter and more adaptable. And while hyperparameter tuning sounds fancy, it's really about giving AI the right tools to learn efficiently. Thanks for watching. If you want to dive deeper into the math or see the full experiments, check the links below. Stay curious, because the future of AI is all about learning how to learn. I'll see you in the next video.